Okay, hi everyone. Thanks for coming to the February C++ meetup. This month I'm going to talking to you about performance and where to find it. So let's begin. My name is Dušan, and for those of you that don't know me, I've been in the C++ Serbia user groups since we started, organizing these meetups regularly. And each year I've been giving a talk, so I didn't want to give my full bio, but it's something that's relevant for this topic. So I did competitive programming when I was in high school and a bit of it in university. I worked on device drivers, I worked on AAA video games, and I'm currently working on ultra low latency financial systems. And all of these require the program to perform in a highly performant manner. So all of these are kind of relevant. So throughout my whole career, I was worried about my program's performance. So what what is the performance? I tried to, as always, find a wiki quote, and this was something from the wiki. It's a measure of performing a job well. It's a definition as good as any. But it's a measure, and that's what's key here. A measure of goodness of performance. So we can represent it with something like this. It's a scale, right? So, you can treat it as some like bad performance and some good performance. So this is what are we going to talk about. So how to achieve good performance and perform well. So let's just um, get flush out all the terminology. So on the left hand side we have like the worst performance where your program doesn't perform, and on the right hand side you have like the optimal performance. That's the maximum measure of performance, and that's what we're striving for in our programs. And to achieve this, like we usually like what's good performance, right? Because we want our program to perform well, and like a ballpark is like somewhere around here, I would say. But that's like your intuitive way of thinking, and for me this is probably good enough. And I intentionally colored it with this shitty color just to good enough for C++ is probably not good, because you are writing for the most part performance critical code. So it always depends on what you're working on, but your definition of good may vary, but it's a bit more to the right? That's what you're trying to achieve. And why am I even talking about this? People have talked about performance a lot, and everybody cares about performance, but I still hear things like this, like today's computers are such powerful machines. You don't need to be optimizing everything. They will just crunch the numbers, or users won't notice a difference. But users actually do notice a difference, right? People have been, going from this idea that like 23 frames per second is good to this idea of 60 frames per second is good. And now like we have 120 and 240 hertz monitors, and everybody is rushing for performance. So users actually notice this. So that's on the user side, but actually performance in terms of computing can also be represented with power and power consumption. So why does this matter? It matters because of two things, like money and time, and time is money. So money, right? And if your code is not performant, you're going to be spending more electricity to do the same job. So that costs you. And like in terms of time, when you're dealing with embedded systems or mobile devices or even cars these days, right? If you're using too much power, you're draining the battery, so you have less time to do the things that you need to do before you need to charge. And that's why people should still be caring about performance. So there's this another story, like AI is a big thing now. When you have ChatGPT, it's like a revolutionary thing, right? Everything is going well until the stocks fell down, right? People are losing money. And why are they losing money? Well, It's because of DeepSeek. DeepSeek came along and the stocks fell. Why? Because they were doing the same thing with less performance, less power needed. So people are like, okay, this is a real competitor. So yeah, a lot of people should be careful about performance and striving for more performance. So when we talk about performance, especially in C++, people usually, go to optimizations, right? You need to optimize for performance, and that's how you gain performance. That's the usual, until this guy comes along. And for those of you who don't know, this is Donald Knuth. He is a recipient of the Turing Award. He received it in 1974. He wrote extensively on analysis of algorithms, and analyzing their efficiency and analyzing complexity of the program. So he cared about performance and still cares about performance a lot. One of his biggest works is The Art of Computer Programming, which is his life's work in several tomes. And there's this really beautiful quote of his that ties it all together. And why is it called The Art of Computer Programming? That says, "Science is what we understand well enough to explain to a computer. Art is everything else we do." So if you think about that, it's really cool how he ties it all together. But usually he's remembered because of this quote. And this is, the premature optimization is the root of all evil. So there are a few things here, evil is the big word. So people don't try not to optimize their code because it's still premature to optimize it. But I think this quote is taken a bit out of context. Why would Knut, who cares so much about performance, say that it's evil? So the actual quote is much longer, right, and carries a bit more context. So the quote is, "Programmers waste enormous amount of time thinking about or worrying about the speed of non-critical parts of their programs." So he felt that the programmers were spending their time worrying about the non-critical parts. And these attempts at efficiency have a strong negative impact when debugging and maintenance are considered. Still talking about non-critical parts of their programs. So he says we should worry about small efficiencies. We shouldn't worry. We should forget about small efficiencies 97% of the time, where premature optimization is the root of all evil. So still he's talking about the non-critical parts of the code when he says that we shouldn't worry about optimizations, right? So he says then we should not pass upon our opportunities in that critical 3%. And this is what we should focus here. When you're working on a C++ program, well, it's a library or a tool or a service or something that's going to be deployed in an embedded system, you're probably more frequently in this 3% than not. So also, this quote is from a paper called Structured Programming with Go-To Statements. And you should see the irony in this. And he saw as well, this title is a clickbait title, even though clickbait wasn't a thing back then. But he used it to show that, even though people in 1974 knew that go-to statements were there was a big discussion, should we abolish them and should we stop using them? So he tried to speak about when you should use it, and it has something to do with performance. So it's a good paper. It's a good paper. So when we're talking about, he said, okay, premature optimization is the root of all evil. So we should first get to a point of maturity, and then we should optimize, right? That's how we, even if you take the, take an out quote at face value, you feel like this, right? It's premature to optimize, but once you mature your code, then you can start optimizing, right? So let's go back to our slide here, like the performance graph, where our program either doesn't or optimally performs and everything in between. So if we discussed what's a good performance or good enough performance. So you're starting on your project, and you ask your like project manager, what should we aim for? Like what should our performance goal be? And more often than not, they're gonna answer like do the 80-20. And 80-20 is a rule that you spend 20% of the time working on the 80% things, and then you spend 80% of the time working on the last 20% of the project. So they're like, just spend the 20% of the time, get to the 80%, and then just finish. So if we take a look at how this impacts performance, it would go something like this, right? We would get this much performance out of our program, and then we stop. And then maybe, even though like to get to the full 100%, you still need like 80% of the time more. You'll probably get like, if the project was like 100 days and you took 20 days to get to the 80% of performance, they will be like, okay, take 2 more days to optimize things. So you can imagine how much optimization you will get there. So this is bad. So we need a way to improve this. And one way to improve it is just to move the starting point. So start from something that's a bit better. So when you end up optimizing it, you get better results. So now we have moved from the good enough territory to good territory, let's say. And so the idea is how we move this starting point. And this is where comes the idea of designing for performance. So when you're designing your system, you should always have performance in mind. And so how do you do this? At the start of the project, you should have clear performance goals, because like whatever you set you intuitively is good, it's going to become into good enough once the deadline starts. So if you set your performance goals clearly, and you track them throughout the development process, you will still have this target in mind and will try to reach this performance target. Because if not, you're just gonna start dialing back, and you're gonna end up in the good enough territory. And in the end, like, choose your tools carefully. I see Ivan here in the audience, so like this question was the one he should have asked himself before he started developing his game in Unity, right? Because in the end, he realized that Unity is just not performant enough for his vision, like for his game. So he needed to switch engines and rewrite the whole thing in C++ and then in Zig. And then, yes, he's still on his journey of, doing it. But like, yeah, things like this, you really need to choose things carefully at this phase, and track it throughout the development process. If you don't have the tools or the time or the resources, at least on like a design level, every time you're adding a new component, ask yourself, how does this impact performance? Because like performance is a global property. Like very quickly, we can like how people usually go at performance is you take a look at what the bottlenecks are, and you optimize the bottlenecks until you end up at a point where you have a uniformly slow code, but it's still bad performance. So it's due to the bad mismatch between the program and the architecture. So you chose the wrong architecture. You chose an inefficient coding style for a particular language. And like when you reach this uniformly slow code point, rewriting is your only option. Like you cannot touch bits and pieces of the code and expect to get performance gains. So performance is a global property of the whole system, and you should be looking at it throughout your design process and development process. So there's also another property of the code that has a aspect of our programs that has the same global property. Does anybody know? Does anybody have an idea of what it is? Like performance and another important topic in C++, especially lately. Enough, but those can be local as well. But this is really, really global thing. Like safety, yes, like safety and security is also a global property. You can easily go through a non-secure program just by having it throughout your code base, and is something that should be tracked throughout development. Yeah. So I found this blog. I mean, I didn't found it. Peter sent me. It's by Benjamin Sputnik. It's from 2015. And he talks about performance. And the blog post is called The Four Horsemen of Performance Apocalypse. Very cute. And these are the four horsemen, according to Benjamin. So it's doing unnecessary work, ignoring constant time inefficiencies, unnecessary generalization, and compound interest. We're going to go into the first two a bit more in depth. So first is like just doing something that you shouldn't be doing and you don't have to do. The second point is just a lot of inefficiencies. The third point is about generalizations. He talks about performance degradation due to like trying to implement a more general thing, but that general thing is much more computationally intensive than your specific thing. And compound interest just talks about how all of these add up together and how easily you can degrade your whole system by just having 2 or 3 bottlenecks. So the first two are more interesting for us because we can do a lot about them. So the first thing he talks about is like using the best algorithms and data structures. So DIGO code complexity analysis, you need to choose your efficient algorithms, your efficient data structures. And that's good, right? Use a better algorithm if you have it. I use an efficient data structure that will guarantee you optimal performance. But you can also do a lot more like smaller things. One is pre-computing stuff. Games do this like by doing shading on the textures themselves or something like that, like pre-computation on the data itself, or calculating things in compile time. With const expert, this is becoming much more easily implemented in C++. So you can use that as well. And another point that he doesn't mention, and I find it a lot, is moving the data, right? The data just sits there in memory and you decide to move it, and that's a copy. And if it's a lot of data, you're just moving it. And maybe you shouldn't be moving, right? Because that can degrade the performance a lot very quickly. So there you need to employ something called data-oriented design. A lot of people talk about this in the C++ community. And zero copies, so maybe disable copy and move constructors if move is expensive as well on your most important data classes, and just not have them copied around. So you can ensure that they are always passed by reference, and then you can use them safely without any performance degradations. Like this thing helped us quite a few times to identify some performance bottlenecks. Okay, and then we have the second point, and that's constant time inefficiencies. So it's things like using bad data structures. So std map has like log n big O complexity for find or and insert, but then it has a bad constant time, right? It's a node-based container. It has a lot of allocations, deallocations. So people just don't use it when performance matters. You have a much more efficient data structures to use instead, depending on what you need. So there are some poor coding techniques without mechanical sympathy. I found that term somewhere. It's quite cute. But what it means is you're writing code that doesn't play nicely with the hardware that you're running on. So it's things like okay, you have an algorithm that does random memory access, like binary search, and then you also have like your CPU caching. So your binary search trashes your CPU cache, or you have like a high entropy branch in a loop, and this messes with your branch prediction. And then you have like unnecessary abstractions. Benjamin talks about unnecessary abstractions, but he doesn't mention the biggest one, and that's the one that's attracting your hardware, and that's the operating system. So things like memory allocations in performant code, people usually don't do them. They allocate things on stack or statically allocate on heap before you start running your critical part of the program, and just use the heap memory as it is. And then you have things like context switches, which are also incurred by the operating system. So when you're writing things that need to be highly performant, you try to avoid them. And in the end, that's why real-time operating systems exist, to avoid these things. And in the end, there is the communication overhead, which gets overlooked a lot. So anytime you're accessing anything outside of your program, that incurs a penalty, and you need to be very efficient when doing these things. And that's where we come to one big point. And I see like a lot of missed opportunities in this field, and that's data format. People store data in different ways in their programs, and they don't care about like the performance of actually storing this data. Like people, sometimes they do, but when they use text-based formats, they don't. Um, so things like CSV or JSON or XML or YAML or Fix, those are all text-based formats. They're quite bad for your performance. They are portable, and they are, but they're bad for performance. They're hard to process by machines. And like the upside was they're easy to process by humans, but this is a text-based serialization format, and I don't see this being easy to process by a human. You need a browser to render this and see what it is. And for all you that are looking at it really closely, it's like the CPP Serbia website. So this is an XML representation of the website. But like, imagine all of this in binary, how much less bytes would it consume and still be portable? Why? Because we have binary formats that are portable as well, but much easier to process by machines. So they use less CPU cycles, less energy, less anything. And you're not gonna be reading through your assembled HTML code by yourself. So why not just encode it in binary? And when you need to do it, you need to analyze your code. You have tools, and you have a lot of these binary protocols. They're made just for this, used across different industries. So let's have a case study. This is a real world thing that we in our company did a few days ago, weeks ago, where we had this HTTP plus JSON API, quite common in the web sphere of things. So we had this third-party middleware software that uses HTTP plus JSON. So DB to the middleware is like TCP SQL, like the database people optimize their things. And then service to database is like a custom line protocol that DB uses for fast inserts. Again, these people care about performance, so they optimize their protocols. But the middleware itself, where it needs to communicate to our service, so service to like middleware to the service, it uses HTTP JSON in both directions. So we were like, okay, if you're already using something like Parquet to communicate to get the data from the database, why not use the same format to get the data to our application? So we went into the open source code and we switched to using HTTP plus Apache Parquet, and we gained 20 times performance, like 20x performance, just by not using JSON, which is amazing. This was in Python, so not C++. Maybe in C++ you wouldn't gain as much performance, but it's still like things like this are really low hanging fruit, especially because like this all change in the open source projects took very little time to implement. It was a very low risk thing, and ended up working great for everybody. So we just got free performance. Yeah. So now we did all the we architected our program well. We chose good tools, so we can now go and mature the program and then optimize it, right? Well, no, like Knut still has some more things to say about optimizations, right? So I'll just continue from the critical 3% from the last paragraph and just continue reading the text. This doesn't appear a lot when people quote Knut about performance, but he says that a good programmer will not be lulled into complacency by such reasoning. He will be wise to look carefully at the critical code. So we need to identify the critical code. And it is often a mistake to make a priori judgments about what parts of the program are really critical. Since the universal experience of programmers who have been using measurement tools has been that their intuitive guesses fail. So what he's trying to say basically is people try to guess which parts of the program are not performing well, and they just try and optimize things. I see this a lot on pull requests where a programmer comes and is like, you ask a question like, why did you write this in such and such a way? And they will answer like, this is more performant than what you're suggesting. Or it's vice versa. You write something and then somebody will suggest, oh, it's much faster to write it like this. And without measuring things, you don't know, right? A lot of the times you don't know. If it's your senior programmer, of course, you listen to him and like you apply the changes, right? But if not, like, feel free to go into an argument and ask things to be measured. Let's measure it, as they say. So measuring performance, how do we do it? We do it. So this is a model that we have in our company that says measure everything, measure precise. And what does it mean? So measure everything means measure every execution. Like no sampling. People usually do, they turn on the measurement tool because the tool has a lot of overhead, and then they turn it off, and then you use these samples to deduce something about the performance, but that doesn't work. You just need to measure everything, because for a lot of systems, your average latency, you cannot even calculate it if you don't, like, it's just not precise. So the other thing is you need to know what you're measuring. So be really careful when you're constructing micro benchmarks, so that you know that something is not getting optimized out. So you're like, oh, this is so fast, but in fact, your compiler just doesn't run anything. Threw away all of the code and is not running anything. And be aware of the measurement error. And like when you're using your tool to measure it, it has a measurement error, and you need to be aware of this and factor it into your measurements. A lot of people have been talking about this, but especially like I like this talk from CPPCon by Emery Berger. He goes really into depth about statistics of measuring software programs. Has a really good anecdote of somebody running the same benchmark on two different machines, and they got two different results for the same benchmark. And the reason was that they were running it under a different user, and the user names were different. So the environment variable like moved the code, like the instruction code in memory. And this ended up that like some code ended up in different cache lines, and like cache was used differently. So there's a lot of variance when you're measuring things. And there are tools that he mentions that will help you measure things correctly. And instead of having a number, you get a graph and you're comparing graphs. Really good talk, really good talk. Never used any of it though, because it seems hard. But feel free to try it and report results on the next meetup. The other really good talk about how to measure performance is this by David Roth. He comes from the same field as I'm currently working in, so trading and financial systems. And he talks about how to count the nanoseconds. So a lot of good information here. He speaks about how to measure time of execution precisely, but also cycles. He mentions like the PSC counter and how do you use it to measure time and cycles, and other hardware counters that help you measure your code in a precise manner. Really good talk. I'm not gonna go through all of it, but this is a must watch before you start measuring things. So some of the tools that are available for you when doing such a work is like Google benchmarks. So you construct these in Google benchmark library. You construct these micro benchmarks, and this will like construct writing these benchmarks. You write them as like your unit tests work for performance, and it ensures that your uh, building blocks of your, like, you cannot measure your whole program in a Google benchmark, but you should benchmark your components so that once they come together, you make sure that every component is as performant as it can be. You have tools like Perf or Intel PCM or VTune or UProf by AMD that allow you to do whole program profiling. And this is like when we get to, okay, looking for hotspots in your program to optimize. But in Linux, you also have eBPF tools. eBPF is a API where you hook into your program and you get to observe it. Um, um, Besides a lot of other things that it allows you to do. And there's this open telemetry eBPF profiler that's available, and try and use it. It's a really good tool. Just, you know, with very, very low overhead, it allows you to get an insight into your program. And in the end, this is not a performance measurement tool, but it's an HDR histogram. It's a data structure for efficient storage of measurement results. So it allows you, whenever you're measuring your program's performance using your own custom tool, you put the results into an HDR histogram. It allows you to live record everything that is happening in your program so you can analyze it after the fact. So if you're looking to write your own performance measuring tool for your project, HDR histogram is a really good data structure to store the measurement results. Okay, so now we can do optimizations, right? Now we measured where they are, and now we can use them, right? Well, no, we need to learn a few things more. So the premature optimization thing is big, right? You've probably heard it a bunch of times. There's even like the wiki page on it. And in the page, if you scroll through the comments, there's a comment that says, oh, well, yeah, premature optimizations are evil. And like, I hate when programmers do like pointer caching for like, it doesn't mention the for loop. I added the for loop just for reference, but he says like indexing is less performant than, doing the pointer caching, but it's much more readable. So I stick for readability, and, pointer caching is it is more optimal, but it's ugly, and it's a premature optimization. And the question here is it an optimization at all, right? Um, yeah, modern compiler, yes. Like the comment was that
Yeah. So there's a person that's kind of prevalent in our community called Stefano, and he does not. No, no. I mean, just no, but he still doesn't.
he doesn't, and that's fine. But like, let's just, it's hard to answer this question without knowing this. What is the thing that's interpreting our code? Probably, probably. But like I said, it depends on the compiler and the hardware that you're executing on. Like, on the compiler side, we have like three big ones, and on the hardware side, we have like a bunch. I try to put them all. And these are only the people that are specifying the CPU architectures, but there's a bunch more hardware manufacturers, and depending on the level of the your program interacts with this hardware, you sometimes need to worry if this is like a Dell or an HP box that you're running on, and what's the setup, and not that it's Intel or AMD. Um, so all of this interprets our code in a lot of ways. So there are these things that both the compiler and the hardware are doing to increase performance of our code, and they do it by themselves. You don't need to do anything. So this is not an exhaustive list. This is just things that I really find cool. So the instruction selection is compiler basically choosing the most optimal instruction for whatever you're doing. Register allocation is basically assigning values to CPU registers in the most efficient way so that things get cached and whatnot. Instruction scheduling is reordering instruction to minimize pipeline stalls. And if that's not doesn't mean anything to you, there's a resource a little bit down a few slides after that will help you understand all. Inlining by the compiler means that you're not calling a function, but you're basically pasting the function instead of a function call. Loop unrolling is basically compiler duplicating the loop body and changing the loop condition in a way so that you more for an effect of more optimally executing this loop. Branch predication. Compiler sometimes generates instructions that have bool flags in them, like CPU. So if this bool is true, then execute this instruction, and if it's not, just skip it, do nothing. And sometimes these instructions help because they are not triggering the branch prediction mechanism of the CPU. And there's also vectorization optimizations that the compiler can implement by itself, right? And on the hardware side, we have like caching, prefetching. People know that what those are. Speculative execution, it's where a CPU tries to execute something in a branch that think it's gonna come true, and this is all for the effect of keeping the CPU pipeline rolling and not stalling. Store forwarding is an interesting one. It's when hardware realizes, like you are assigning a memory store operation, and you have another instruction in the pipeline that's going to use the value. So the CPU will kind of store it in a register and give it back to the instruction, or have circuit that's going to get the result back to the next instruction and use it in the pipeline. Microcode fusion. I hope that you knew this, but CPUs, they are implementing an instruction set with an instruction set of its own called microcode down below. So you are looking at your x86 or ARM instructions, but the CPU has its own instruction set internally. So it's doing the same thing compiler does. Like, it's trying to optimize, like he's trying to compile the instructions into microcode, and it can do a lot of transformations to make this more optimal. And the register renaming is storing things in registers to eliminate fault dependencies. That's all I'm gonna say. And again, pipeline stuff, keeping the pipeline rolling. Okay, so what does this mean? Like, for us to be really, really, really knowledgeable about how to optimize our code, we need to know our stack. So this is the main paper that everybody should read, and you should realize this by its title. It says what every programmer should know about memory. It's from 2007, but it's still relevant. Like all of this information is highly relevant even today. You can use Compiler Explorer to explore how your code gets compiled, and this is knowing your compiler kind of thing. You can read documentation. It's a foreign concept to all of us, I know, but it's doable. And a lot of cool things are there. Like the lightest read is probably the C++ core guidelines. There are short bits, tips on how to improve your. There's a whole section on how to improve your C++ code performance. There's you can read library documentation, and you can read hardware documentation. Like every hardware that's been released comes with a manual and a spec sheet, and you can read through it and realize like what it can do and how optimal to use it. And in the end, you can read your third-party source code. This you can read it for understanding the performance implications. Like maybe your library is doing something in a specific way, and you need to use it again in a specific way for it to be for not to lose performance, right? A lot of times people misuse the library and end up getting performance degradation due to that. But also, like if you have some really good optimized libraries, you can get ideas on improving performance in your own code. Like all the performance like tricks that are used by your library can probably be applied to your code as well. So it's a really good resource to have. And in the end, like there's this talk where you can learn a lot more on what optimizations are available and how what your hardware actually is. But like this speaker took this slide from a different person, and that's from a blog post, so you can probably read that as well. Huh? Yeah. It's a very good. It's a very good. Yeah. So, um, just to convince you again why all of this is important and that it's all achievable. You can take a look at two screenshots. Like these are running on the same hardware. One is a game from 2007 when the console launched, and the other one is from 2013, like at the end of the console's lifetime. And you can see they look look very different. Like this one on the right looks much more pretty, and that's because people are spent a lot of time learning about this piece of hardware and learning how to optimize on it. So you can get from this to that if you really optimize your code. And this is the impact you're going to have once you flush all of those things out. So in the end, we are getting to the point where we are going to talk about optimizations. So that's when you need to roll up your sleeves. So the tools are not helping, and you need to do things on a micro level to increase performance. So what can you do? So your instruction selection on your compiler is bad. You can do better. So you can use assembly or intrinsics or something, to improve performance on a specific hardware. For some reason, your compiler doesn't know how to do it. Maybe it's better to submit a patch to the compiler so it learns. But yeah, you can write it yourself as well, and then it will end up in a GPT brain, and then it will get reapplied to the compiler. I think that's the way it's gonna go. Inlining, you can just inline your code manually or use the inline keyword, and templates get inlined easily. For loop unrolling, people hand unroll loops. For branch predication, again, use intrinsics where you think they're good. And for vectorization, you can use like assembly intrinsics or Google Highway. It's a good library that helps you do vectorization. And on the hardware side, you cannot do anything to hardware, but you can give some instructions on and give some pointers on how to increase the performance through some directives. But you need to be really careful when doing this, right? It's like, you're turning off the autopilot and you're doing everything manually. So you really need to be careful and take a systematic approach. So you need to measure a lot. So you need to measure before your optimizations and then after to see if there are optimizations at all. And also you need to measure all use cases. Like you might be optimizing for one use case, but you're really destroying performance in another use case. And there's always this trade-off between correctness and optimizations. So it happens, you're optimizing, and you end up optimizing, but by not doing a thing that you should be doing, right? So you need a really good test coverage if you're going to hand optimize something to ensure that the program correctness is still there, because that's the most important part, right? And in the end, if you're looking to optimize things, you can talk to this guy. He's right here in the audience. He speaks a lot about performance and optimizations and all of the things that I've mentioned. He writes about it on his blog. You can go check that out. You can you can YouTube search his name, and a lot of talks will pop up. And watch all of them. They're really good. And they teach you about the thing that I skipped at the end, right? And how to actually perform these optimizations. But the fact is that I just don't do this stuff, right? I don't actively work on optimizing my code. I usually just rely on good design, and I hope that from now on you'll do that as well. Yeah, that's it. So, any questions, comments, anything? Oh, this is really bad.
Can you talk a bit about coordinated omission when doing benchmarking?
About what?
So coordinated omission is a thing that can happen when you're benchmarking your code, where uh, the setup is actually causing you to not see performance problem. Meaning, for example, if you're testing the service and we're doing a ping pong test, we could have a spike in latency, and if it's a ping pong test, it's only going to impact one event. But in reality, you have a stream of events that is happening. And if you have a large latency gap, you're going to get queuing. And coordinated omission is a name for when manual testing is just omitting these real world events.
Yeah, sure. Like that's exactly what I wanted to say by when I said know what you're measuring, right? You really need to be careful when constructing these micro benchmarks, uh, because like you said, if you're avoiding queuing, you're avoiding queuing. And like on the topic of queuing, it's not something that you can avoid. Queuing just happens, and it's due to the fact that your system is slow and that the rate of arrival of requests is big, and your system cannot keep up. You have queuing. That's the reality of it. So, anything else? Yep.
Well, because you name dropped me during the talk, I just want to say that like when you mentioned that I used Unity and I wanted to do I should have probably rewritten everything, but the thing is that I didn't know, so I had to learn all the things in Unity first, and that often happens. Like you use libraries and you don't know, because you don't want to go into optimizing, because you're completely unaware what exactly they're doing, right?
Mhm.
So there's also this factor of like what you know, right?
Yep.
And how much you can actually optimize.
Yeah, exactly. And that was like the point I was trying to make. You really need to know a lot before you start optimizing, because there could have been a lot more things you could have done before you're getting to this point of, okay, now we're optimizing.
And there's also this talk, there are no zero cost abstractions. I can't remember who it was by, but
Triangle curve.
and that one is a great like comparison of like that.
Yep.
Like how much it's not just about abstractions, but like you always have to compromise somewhere.
Yep.
Whether it's knowledge or manpower or yeah. So
Yep.
that's
Yep.
good.
Exactly. Like it's really a trade-off thing. And you need to be aware of where you're trading it off. But a lot of the times people just assume that they're doing one type of trade-off, but they're unaware of the other consequences. So they end up paying for it a lot later, like you did with the game engine, right? You're like, okay, I'm gonna write it in Unity because this is something I'm familiar with at the moment, and it's gonna be fine. People are doing it, but at the end, and then you decided to use another tool because you were like, oh, it's impossible to do it in this tool. But probably, maybe, it, yeah, it is. It is. Unity is, yeah. No, you definitely can do it. It's just it's written in C sharp, so you have less control versus when you're writing in C++. But as I remember, everything.
Yes, but the problem is always that well, yeah, this is also an optimization problem where because the scripting is done in C sharp, the engine itself is implemented in C++, right? But there's a layer on top which is C sharp, which is what lets you interact with the engine. So the problem is that, of course, initially it was imagined to be like, oh, you're just going to do some light things and call light functions, but then you actually end up doing everything in C sharp, like a lot of expensive stuff, and that is why it's always a problem. This is all. This goes for all game engines basically, because most studios have some kind of a scripting language on top, and the designers or people who are uh, you know like on the light side of programming will start abusing the scripting system, and then the optimization is going to be terrible because of that.
Yeah.
So in every company, like, you need to have people who are good programmers that work with designers and will implement the stuff that designers design for really good optimization. But yeah, and that's the problem with like most engines in Unity specifically, because you have to do everything in C sharp, and there is no source code available. So I mean, you can have source code if you pay a lot of money, but yeah. So the only if you really need to do, but the thing is that uh, it's if you need to do something very specific, then it's probably much better to have your own engine, like make your own engine.
Yeah.
Because for most things, Unity is pretty good. Like, yeah.
But also when you mention scripting, I think that's how Python was envisioned as well. Python was envisioned to be a scripting language, and every performance critical bit is going to be implemented in a lower language like C or C++. And then people ended up writing web services in Python. You're optimizing performance there instead of just moving to a layer below.
I mean, JavaScript as well.
Yeah.
It has a script in it. It's like a scripting language for the browser, but now everything is done in it. So
Because people spend a lot of time optimizing it. That's why.
Yeah, so you mentioned that at your company you measure everything. How do you do that? Do you do that as a part of CI/CD process?
No. Well, in CI/CD we run micro benchmarking, and we should collect results. They just stay there, and nobody looks at them. And then sometimes we have a performance degradation, and then we go look at all the runs and see where it happened. So in every commit to main like branch, we do run micro benchmarking for everything and collect the results. But also we measure everything in production. Like every critical piece of code and even non-critical piece of code is instrumented. So anytime it gets executed in production, you get to see how much time it took to execute it. And then we collect these metrics live. So even when you're developing, you get to see these metrics and you observe, and then you move to a production system, and then you observe again, and then that's how you track performance of the whole system.
Well, does it impose any overhead running that over production?
It does, but that's what I was saying. Like when you're using your measurement tools, they really need to be low overhead. So things like we in-house have a custom library for this, but also like if you're using stuff like eBPF, you also have a very low overhead. So if you invest into like either your own, or you can find a library that has a really low overhead instrumentation, or you write your own, really invest time in this if you care about performance, because it pays off a lot. Because having the observability across your entire system helps a lot when dealing with bugs and performance issues. So really allows you to get to know your code in a good manner. Yeah, it depends on the load. And like Peter mentioned, queuing is something you cannot avoid. So when queuing happens, spikes happen. But the system is usually fast enough, so it just processes everything. And like we measure like all the nines. So we really care about tail latency. So we measure like 99% of all requests get executed under this amount, and then 99.9, 99.99, 99.999. And that's where we stop, but we also track the maximum, and that also gives us an insight into where things are.
Well, to add up to that question, did it ever happen in your experience that that the measurements actually gave you a wrong measurement because they were interfering with the times?
We did have one bug. It happened when we were measuring round trip times for a request. So a request is coming in, and you want to track the time so that you can measure the response time for this request. So you propagate the time when request entered the system. You propagate it alongside with the request, like in a header or something, right? And it goes through the entire system. And on the way back, you look at the number that was stamped in the header. You look at the current timestamp, and you subtract these two, and you get the amount of time it took for you to respond to this request. And we had a bug where we mistakenly forwarded the time from the previous request. So a request comes in, we process it, we take the timestamp, we push it through the system. But when we want to append to the header, we don't append the timestamp of that request, but the previous request. Yeah, yeah, but something like this. No. The request was timestamped correctly, but yeah.
We propagated everything correctly. The thing was that like because of some internal library that you're using, you were storing that value in some variable, but you were reading the value before you've stored it. And reading before storing it got you the last one,
Yeah, I know.
which is just
So basically, we appended the last one. So like that was a bug. It was really hard to track down. Took a lot of time.
yeah. But like the main thing is what Dušan mentioned in the talk. You need to be aware about the precision and overhead of the measurement that you're doing. Like if the measurement tool that you're doing is adding 50 nanoseconds, then you shouldn't measure anything that's in nanosecond range. And that's the way you come to a point where you're certain that the measurement is not going to input the actual thing that you're measuring. I like the problem with using conventional tools is if like the measurement system adds 2 milliseconds, you cannot measure anything that's faster than 10 milliseconds. And then if you're doing game programming or anything, it probably you want to be faster than 10 milliseconds.
Yep.
So you mentioned in a slide that if everything is slow, then you need to rewrite everything. What about if everything is fast? So you've already developed for a long time. You have a good whatever code that 3% has been optimized very well, but you still need to go faster. How do you find those efficiencies?
Well,
You have like I don't know, a lookup function that is called 1,000,000,000 times per frame or something like that. How do you find those small micro optimizations that simply add up to like 1%, 2%?
like so. Look, it's contradictory, right? You say everything is running fast, but it's not running fast because it's slow. You still need more performance. So the conclusion is your program is slow. It feels like you've optimized everything, right? But you're uniformly slow. That's actually this point, right? So a rewrite there is necessary. Like it's really good that you're mentioning this. Like if you have this function that's called 1,000,000 times, it's gonna pop up in your like usage statistics a lot. Like, oh, this function takes this a lot of time, but it's okay because it is called a lot of times, right?
Yeah, but it's not gonna show up because it's a 10 nanosecond function.
But it actually has 10 million times. Like,
Yeah, but your profiler is not gonna pick it up because you're at
this.
depending on your instrumentation costs. Because if you add like the lowest I've seen is like 5 nanoseconds of instrumentation per call, and if your function call is lower than that, you're not gonna.
Awesome. Lost. Yeah, but also, yeah, but also like you have like the eBPF thing, and that's really really low overhead, so it will catch things like this. Oh, it's a eBPF is like a Linux kernel API that allows you to write a program that's going to hook into your program and do something on the side or in the program itself. You can. eBPF like VTune is paid, right? So this is a this this is a perf has a lot of overhead, right? EBP. No, that's a lot. eBPF does things even cheaper because it's sidecar. Did like I don't know the mechanism of how eBPF actually works, but as I understand it, it's doing a side thing. I don't know. It basically monkey patches your code in an optimal way. So it injects instructions into your program that allows you to do anything. So people use dbpf to write profiling tools that allow you to. You can debug your own program as well through the same API. Yeah. And like this tool by the Open Telemetry guys is actually a profiler implemented in eBPF that you can use on your own program. That's really cool. Check it out.
Can I ask? You hear me? Will?
Yeah.
Yes. You mentioned instrumental, you mean profiling, instrumental profiling. I just used a little bit profiler, and there were two options: instrumental, Microsoft Profiler, instrumental and sampling. You mean there are two kinds of profiler? Is that what you mean, man?
So I really haven't worked on in Microsoft stack for a long time, so I don't know like all the options there. But basically, I'm not sure what you're referring to, but a lot of profilers get you to choose if they're gonna do the sampling thing or just gonna measure everything. Measuring everything usually incurs a lot of performance cost. So, and if you use the sampling thing, you miss out on a lot of data. So yeah.
Okay, another question about the speaker. One of the persons asked about talk about game engines, and so this is the section about that it's hard to think as a scripting language and there are internals of game engines.
Yep.
So can we call it? Can we call almost all game engines, premature, optimized? So
Yeah,
not accounting users.
yeah, they are. They are definitely. I think that's the way it needs to be. Like you really need somebody to go into really details for you and optimize a lot of things, so you don't have to. Like even compilers and all the compiling optimization techniques that they apply is basically them doing the what people previously could consider premature optimizations. Now the compiler just automatically does that for you. So you get to write your own, semantically correct code, and the compiler does all the, ugly stuff below.
So everything premature is evil.
Okay, thanks everybody. There's beer in the fridge. There's also whiskey. And